Everybody, this is Mr. Folly, and welcome to the second podcast, Big Idea 2. Intramolecular forces, so these are forces within molecules. IMF is intermolecular forces, so don't use IMF for intra. Okay, so covalent bonds form molecules. Ionic and metallic bonds do not. So ionic and metallic bonds form lattices. Okay, and ionic bonds form formula units. Okay, but they both form lattices, but formula units are what you call an ionic lattice. The differences between covalent bonds. So now we're just focused on covalent bonds. First thing is bond order. Bond order is really simple. You got single bond, you got double bond, you got triple bond. So you've got yourself something like a single bond like H to H. And notice how I got 2 points in that line. There's 2 electrons that are shared. The bond order is 1. These are the longest and these are the weakest. A double bond. So that might be like, I know I'm given diatomic elements for all these, but that way I don't have to worry about other bonds. So notice how there's 4 electrons in a double bond. It's bond order is 2, double, bond order is 2. It's shorter and stronger. So I use the analogy if something is shorter, it's going to be stronger if I have like a stick I'm going to break and it's like 3 feet wide. So it's like wider than my shoulders. And I bang it over my knee. When I bang it over my knee, it's pretty easy to break. But if it's really short, it's like about as wide as my knee itself. I go to hit it on my knee, it's harder and it just hurts my knee. So that's it. Triple bond, same basic idea. Again, welcome to another diatomic element, and you get a triple bond right there. All right, next thing I want to talk about is energy wells. Well. So an energy well, and this picture has to be on your test. So this is a gots to know how to do it thing. This part right here compared to this part right here. This one is stronger. So notice how stronger is downer and lefter. Downer is a deeper well. Notice this is energy, and this is a negative value. This, I'm going to erase my circle here. Notice how this is negative 436. A little zoom in for you. Negative 436. Okay. And then this one would be stronger because it's lower. It releases more energy. Okay. So the x-axis is the distance. See how this is 74? This one, 74 might be here for picometers. This might be 50. Excuse me. The radius is smaller, so the x is distance. And notice how distance and radius are the same. Energy goes up really close. So notice how as I go here, this is approaching infinity. And the reason why is if this is nucleus 1 and this is nucleus 2, they're both positive. And if you put 2 positives close to each other and keep getting closer and closer and closer and closer, what's going to happen is that repulsion goes up exponentially because it's a radius squared deal. When you go really far away, like over here, I'm going really far away, it approaches 0 because remember, bond energy still and always is Q1, Q2 over radius squared. And as this approaches infinity, bond energy approaches 0. And as radius squared approaches 0, right, bond energy approaches infinity. And that would be that part. And this would be this part. All right, deeper, stronger, blah, 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 blah. Bond energy. Okay, so taking a look at bond energy. Positive values because it's the energy to break a bond. So the definition of a bond energy is the energy to break a bond. That's why it's positive. Smaller atoms have greater bond energy. So looking right here, there's a weird little quirk in here. O to Cl versus O to I should do this, right? So O to Cl is smaller, and this is larger, but there's some other weird thing that happens. You would think those would be flip-flopped. But once in a while, I guess that's the exception that proves the rule. You do not need to know that exception, but you should know that expect smaller or bigger is weaker. Okay. Wait, that's just part of it. Smaller atoms, more polar atoms have greater bond energy. So remember, more polar means bigger Q, because remember Q is charged. All right. Sigma and pi bonds. Sigma bond is a single part of a bond. Pi bond is the double part of a double bond, or the triple part of a triple bond. Now, it doesn't have to be labeled quite like this, but see this part in the middle? This is sigma. That's the symbol for sigma. And these guys up on top are going to be pi bonds. So if I were to label this, I'd have sigma, and then I would have 1 pi, and then I would have another pi. So, uh-oh. All right, good. Sorry, I had to pause. Last time I paused, I got stuck where it didn't work. So you need to know that the sigma is the single part of a bond, and that all bonds have, oops, all bonds have sigma. Pi bond's the double part of a double bond and the triple part of a triple bond. All right, going to hop into a couple of these and we'll be done. So big idea 2.3, ionic compound structure and functions. We're going to talk about ionic. So before those were only covalents, these are now ionic. So if you look at these, notice how this has a beginning and an end. That would be a molecule, okay? These don't have that regular beginning and end. You see a network that goes on and on and on and on and on. So ionic compounds, are made of ions. Positive ions are called cations. Negative ions are called anions. Try not to mispronounce those. They make us all look bad. So they're not cations nor anions. Structure. So the idea is you arrange it so that, see, this structure has issues, right? I've got negatives. I'm sorry, I got two positives next to each other. It doesn't work. So typically what you'll see is positive, negative, positive, negative, positive, negative, positive, negative. And see how this has all of these things they're attracted to. And then slam that into a little three-dimensional thing. So you've got this super strong lattice. All right. So it's very strong. So you've got huge positives and negatives. That's huge Q's as far as Coulomb's law goes. And you have a lattice. So you've got a bunch of huge Q's. Properties, they're brittle. So if I took my positive, negative, and I had negative, positive, and I shift it just a little bit. So if I took these and moved them down a little bit, instead of being super strong, awesome bonds, I now get negative, positive, and that repulsion is going to break. And they're going to have, so shift, the lattice, and the charges line up and repel, and you get cleavage lines. So it'll have a specific shape how it breaks. They have very high melting and boiling points. Hey, that's because of strong bonds. They're non-volatile. They don't evaporate. Hey, that's because of strong bonds. As solids, they're insulators, which means they're non-conductors. Conductivity is a flow of ions. That's of electricity. Ions are locked in place. Why? Strong bonds. So remember how I told you last test was all about size and nuclear attraction? If you're talking about ionic compounds, you're going to talk about strong bonds. As liquids, they're conductors, because as liquids, those ions can now flow, right? And if you get ions that can flow, hey, that's the definition of conductivity. As solutions, they're conductors. Why? The ions can flow. All right. And many, but not all, are soluble in water. Positive and negative ends of water attack the positive and negative ends. So if I draw a quick little bond here, and I'm going to start attacking a whole bunch of water molecules on here, do you see how, in this case, I've got 4 water molecules trying to break this one apart? And that could happen. So it depends on how strong that ionic bond is, the Q's and the size of them, and how much that'll get them. So many are soluble in water because the water, remember, water has a positive and negative end. The chin of Mickey Mouse is a little bit negative, and the ears of Mickey Mouse are a little bit positive. All right, ranking properties. Charge matters most. We talked about this a smidgen on our last test. Bigger charge is stronger bonds, and size from the periodic table, smaller is a stronger bond. So in this case, MgCl2 would win because of the Q's versus Na positive and Cl negative. All right. Alloys and metals, and we're all done. Woo-hoo-hoo. So alloys and metals, properties of metals. Metals are malleable, and every explanation for this is about the non-directional covalent bonds. So the cloud of electrons called a non-directional, So a non-directional covalent bond can reform easily when particles move. So we talked about in class, if I change the shape of the room when we were in a mosquito world, then the mosquitoes would change and we'd still be bonded together. Ductile means you can be changed into wires. That means basically these, I have a hard time telling the difference between them. And I've never fallen into a problem with that. Think of ductiles as being malleable into a wire. They conduct to solids and liquids. Ions, electrons in this case, can flow. They have variable melting point and boiling point. That means it's unpredictable. They never dissolve in water. And the strength of bonds are found by the size of the electron cloud and the attraction of the nucleus and the number of protons. There's two types of alloys you need to know. One of them is interstitial. Interstitial means inside of or between. See how these guys are inside of it? Whoops, I didn't mean to pull that out. Small elements fit inside of them. And substitutional. So see how these are almost the same size? I just put small. I meant to say same. And really I'll say similar size. And these are tiny. And then use the atomic size to identify the type of alloy. If it's similar, it's in the same period, it's substitutional. If very different period, it's interstitial. And we are now going to have an interstitial break, and I'll see you in class. Toodles.